Welcome back. Before the break I had asked, for a zero order reaction, why is the unit of rate and rate constant the same? To answer this, recall the rate equation for a zero order reaction. Rate is equal to rate constant multiplied by concentration of reactant raised to the power 0. This implies that rate is equal to rate constant. Simple, isn't it? Now, when you look at a chemical reaction, what kind of information do you get from it?
Here is a balanced chemical reaction of nitric oxide and ozone. We can tell that the reactants are nitric oxide and ozone, and a chemical reaction between them leads to the products nitrogen dioxide and oxygen.
But there is no information about the process by which a reaction occurs. So chemists have devised a method to denote the step-by-step pathway by which reactants change into the products. This is called the reaction mechanism. Each step in this mechanism is called an elementary reaction. When the reaction mechanism is described in great detail, it can tell us about the way in which bonds are broken and the changes that occur in the relative position of atoms during the course of a reaction.
Let's look at the rearrangement reaction of methyl isonitrile into methyl cyanide, as well as the reaction of nitric oxide with ozone to form nitrogen dioxide and oxygen. As you can see, both these reactions occur in a single step. Such reactions are called elementary reactions, and the number of reacting species that take part in an elementary reaction gives the molecularity of the reaction.
Reactions can be classified on the basis of molecularity. If the elementary reaction involves only one reacting species, the reaction is called a unimolecular reaction.
As you can see, the conversion of methyl isonitrile into methyl cyanide is a unimolecular reaction.
If two reactants are involved in the elementary reaction, it is called a bimolecular reaction. If three reacting species undergo simultaneous collisions to give products, then it is called a termolecular reaction. And those with more than three reacting species is called a complex reaction. I am sure you can now easily tell that the reaction between nitric oxide and ozone is a bimolecular reaction. Now, some of you may ask, what about reactions with more than two reactants? Well, the probability of that happening is relatively lower. Why?
Just imagine rolling two tennis balls on the floor from opposite ends. It's easier to cause their collision. As the number of balls increases, it becomes tougher to bring about a collision of all of them together.
Now tell me, is it possible to have a molecularity of 0? It's elementary, my dear friend. This is an impossible situation. How can you have a reaction without any reactants? Let's now consider the reaction between nitrogen dioxide and carbon monoxide. As you can see, there is a discrepancy between the predicted and actual rate law.
The experimentally determined rate law shows that the rate of reaction is directly proportional to the concentration of nitrogen dioxide raised to the power of 2 and is independent of the concentration of carbon monoxide.
This suggests that the reaction does not occur in a single step. Rather, it occurs in two steps, out of which the first step is the slow step and the second step fast. How does this difference in speeds of reaction affect the overall rate? Think back to the hourglass we saw in the beginning of the show and keep thinking.
Just as the rate of sand flow depends on the flow through the narrowest width of the hourglass, the overall rate of reaction depends on the slowest step. In the reaction we just saw, this slowest step is step 1, in which only nitrogen dioxide is involved. The slowest step is called the rate determining step in the proposed mechanism.
I am sure you can also now deduce why carbon monoxide does not appear in the rate law, and that is because it is not part of the slowest step. Thus, the overall rate law is the rate law for the rate determining step or the slowest step. Such a reaction, which takes place through a sequence of 2 or more consecutive steps, is called a complex reaction. The order for a complex reaction is the order of the slowest step. Remember this just in case it comes in your exams. Now, let me take a very interesting question from a student.
Does the decrease or increase in the concentration of reactants affect the second order reaction also?
Good question. For a second order of reaction, the rate is equal to the rate constant multiplied by the concentration raised to the power of 2 as per rate law.
Let us assume that if the concentration of reactant A increases threefold, then the new concentration becomes 3A. As a result, the new rate becomes K multiplied by 3A square. This can also be expressed as 9KA square. From this, it is clear that the rate increases 9 times for a threefold increase in concentration.
Now it's time for you to step up your concentration and get prepared to face some challenging questions, because coming up after the break is Exam Decoded.